and I have to stop again. So,
Now I'll start again, no? Otherwise it will be a very long file.
sir, I had just started it when you joined.
No, you joined, huh? Okay. Okay. In the last two classes, we have started the journey towards learning the best architecture which can be used for a CPU meant for microcontrollers. Among the many companies who are in the design of the architecture, we understood that the ARM architecture is very popular and is being currently accepted by top microcontrollers in the world. And we have discussed that ARM is into the business of only giving the architecture as an intellectual property. They are not into the manufacture of the microcontrollers. Also, we understood that ARM is not going to manufacture the microcontrollers, and they release a lot of CPU versions or CPU core versions, so which is available for the industry to purchase and manufacture. Example, ARM7, ARM8, 9, 10, 11. So in that, we are taking one architecture, ARM7 architecture, and studying in detail about that architecture, as we are going to use that architecture-based microcontroller to build our projects. As I said, ARM architecture is a RISC type of architecture. It is completely different from the CISC architecture, because CISC architectures were meant for CPUs used in laptops and desktops, whereas ARM architecture is meant for CPUs used in the microcontrollers. So we have discussed there are four to five points. The moment I say RISC, you should be able to tell that, yeah, because of RISC, these are the 5 advantages it has. So what are the advantages? I said all the instructions in ARM7 is of 32 bits. Most of the instructions are executed in one cycle. Only the load and store instructions access memory. All other instructions, data processing instructions, store their operands in the registers so that it can able to complete the instruction execution within a cycle. Since the number of instructions supported by the architecture is less, the hardware complexity and the die size of the architecture is very minimal and the cost is less, so that since the transistors are less, the power consumption is less, so that it can operate from the battery. So these are all the advantages what you can see. So when you say it's a RISC architecture. Now, so there are 12 highlights ARM architecture compared to the other RISC-based architectures supported by other companies. So first is ARM is a RISC. Second is, as I said, whenever you want to communicate between the ARM core and the memory which is present outside the ARM core, you basically require the bus. So the bus, what is we have used is this bus I'm talking about. So this is the ARM core. Your instructions are stored in the memory here, which is outside. This is the bus. This is a bus. So ARM core, 7 core, support 32-bit data bus. It also supports 32-bit address bus. So what is the size of your memory? The maximum memory the core can support is 2 to the power of 32 addresses are there. That is the memory map of ARM core. That does not mean that complete 2 to the power of 32 memory is present in the chip. It is like having a site. Site has got 1,000. A big locality has got 1,000 sites. That does not mean that I have to construct all the sites. I may require, I'm affordable. So for five houses, so I may construct 5 houses, even though the sites are 1,000. So that means that the core is capable of addressing large memory locations, but the microcontroller manufacturer cannot afford to put that much of memory because of the cost involved. So 2 to the power of 32 is the memory supported, but that much of memory is not given. So how much the memory they provide? They provide only less, say 512 kilobytes, like that, the memory they provide it. So whenever ARM core wants to read from the memory, the size of this bus is 32-bit. The size bus is 32-bit. So ARM core supports 32-bit data bus. Now, so coming back to the features again, ARM supports pipelining in the sense the fetch, decode, and execute, which are the 3 important things to run your programs. All 3 happens parallelly. And the 4th point, as I explained yesterday, whenever your microcontroller provides a very less memory for your programs, what you have to do is you have to reduce the number of bytes required for every instructions. So to support that small size embedded projects, ARM provides what is called as thumb instruction set, so that high code density can be achieved. And the 5th point I said is most of the ARM microcontrollers or the ARM processors support operating system, what is called real-time operating system, which can be loaded into the ARM microcontroller. Any microcontroller which has to support operating system means the recommended is you have to provide 2 important blocks called as memory management unit and memory protection unit, so that multiple programs can exist and run parallelly, and the OS kernel can also run parallelly. So they can run independently and providing the security and the privacy to the individual programs. ARM supports it. ARM also provides cache in every core so that the throughput of the system is better, improves. So ARM7 has 8 kilobyte cache. As I said, whenever you want to do a microcontroller based project, a lot of software and hardware is involved. If the project is not working, the problem may be in the software, the problem may be in the hardware. It is very challenging to debug such projects. So you should stop at the hardware level also. You should stop at the software level also. See that what is happening at the board level. You should be able to capture the data. You should be able to see the registers. You should be able to see the memory contents. For that, a proper hardware-based debugging is required. So which is a part of the microcontroller. It is not the software part. It is not the simulator you are running. It is a debugging at the hardware level. So most of the top microcontrollers today, they provide what is called Jtag interface. It's called Joint Test Action Group. It's a committee or propose this debugging support. So since it's accepted by many of the companies, a lot of third-party debugging tools is also available. So Jtag debugging is supported by the ARM microcontrollers. It provides a fast multiplier unit to enhance the time taken for multiplication. Whenever you use DSP, whenever you ARM microcontrollers for signal processing, for audio signal processing, for video signal processing, you want to perform some Fourier transforms on the signal data. So then it is always better to perform these algorithms at the hardware level. To support this type of signal processing, DSP is provided as an option in some of the cores. Many times, ARM-based systems are used for game development, game playing. So since most of the programs are written in Java, it's always better to support Java bytecode execution at the hardware to give real-time experience. As I said, the microcontrollers generally are integer-based systems. Their instructions are supported to perform integer arithmetic. So whenever you want to perform the floating point numbers, whenever you want to perform the floating you have to do software conversions. So to support that conversion, hello, am I audible?
Yes, sir. Sorry, your voice is breaking.
So support, yeah, I think now it's better. To support this conversions, a lot of software code has to be executed. So for that, if I'm able to provide a facility at the hardware, if my instruction handles the floating point numbers, I have a unit which can directly execute that instructions. If my instruction handles the integer numbers, yes, already the microcontroller is capable, it can execute it. In earlier 8086 based systems, that is Intel, they were giving a two processors. One processor is 8086, other processor is called as a co-processor, 8087. So the motherboard, there was a space was there. Those who are interested to increase the speed of execution, the speed of performance of the personal computers, they can purchase the co-processor and put on the motherboard. Co-processor is nothing but floating point processor. So when you write a program, so if it is a floating point, it will be executed by the co-processor. If the instruction is for integer, it will be executed by the normal processor. So like that, if your hardware is capable of executing the floating point instructions, then the throughput of your total system will be more. So that is, it takes less time to execute. So mathematical or engineering intensive applications. And the last is synthesizable. That means that the ARM core, which is supplied as an RTL code to the companies, or can be editable or not editable. If it is editable, in the sense they can able to do certain changes in the RTL code or the design supplied by the ARM, we call as that core a synthesizable core. So these are the 12 facilities which are popular for the ARM cores or ARM CPU based systems. So not all the 12 features are presented in every core. I said 7 is there, 8, 9, 10, 11, so many core versions are there. And each version, there's a varieties are there. Not all the cores support all the 12. That is why when they release a core, a particular version, they will indicate next to the number, for example, 7, after the 7, they indicate certain numbers, letters. So those letters indicate what among the 12 features are included in that particular core. Let us see one core which we have used in the LPC 2148. That is a microcontroller we are going to study. So ARM7TDMI. So this is the core which has been used in the LPC 2148 microcontroller by NXP Semiconductors. As I said, apart from the number, they indicate what is called like this, which clearly says what is the facilities provided by this core. Not all the 12 facilities are listed. First one, T. T means ARM7 TDMIS core supports thumb instruction set. So first one. D. ARM7 TDMIS core supports Jtag Debugger. M means it supports the multiplier. The I is in-circuit emulator. This is another facility for debugging the hardware-based systems. S means synthesizable. So that means that ARM7 TDMIS supports the following features in its ARM core. So this is how you should understand. From now onwards, any core you find out which is used in a microcontroller, you should be in a position to identify these are the features supported by this core of ARM company. So now we have understood that. So ARM7 TDMIS has got the following features. Now, so let's move forward now. Now we have understood what is ARM microcontroller, what are the features of ARM microcontroller. Now we will choose one core, one core from the ARM. Let's study in detail about that core. So which is a core we are going to choose? ARM7 TDMIS. So this is the core we are going to study for the next 30 minutes. What is present inside the core? How to understand them? Then how do you write assembly programs for this core? Now, whenever you take any core, these are the blocks which are present in the core. So what are the blocks are there? So one is it has got an ALU. So ARM7 TDMIS core has a 32-bit ALU, which can perform addition, subtraction, multiplication, logical operation like AND or XOR, rotate operations, and the shift operations. So these are the operations you can able to perform using 32-bit ALU of ARM7 TDMIS. Whenever you perform the operation, I said the data will be provided most of the instructions by registers, because whenever your data is in the registers, the time taken to fetch the data from the registers and execute will be very less. Look at the registers. It provides one data, another again provides another data. That means that registers, whatever you have, supply the two operands for every instructions. How many registers you have? So totally 31 32-bit registers are there, plus 6 status registers are there. So totally 37 32-bit registers are present in a ARM7 TDMIS architecture, or ARM7 in general, I'll say. So if somebody says ARM7, how many registers are there in the quiz? Is a 37 32-bit registers are there, and these registers supply the data for performing your arithmetic operations. Whenever you are supplying the data, there is a facility is there. You can take the data from one of the register, shift the data, and you can provide it. That means that if I want to add the two numbers, one number I'll take from one register, another number I'll take from another register, shift right or left for a number of bits, and then use it for addition. I can do that one. That is why barrel shifter is provided in the path of one of the operand. I can use it or need not use it. I can just add the two numbers without shifting, or I can add the two numbers with another operand with a shifting operation. That is the beauty of the barrel shifter. So within single clock cycle, you can perform the shifting and arithmetic operation. So how many bits I can shift? 32 bits I can able to shift left, right, or even I can rotate the number. Then it provides a multiplier so that you can able to perform a faster multiplication, because it is not a part of an ALU, it is a separate unit, so that it has got an extra hardware. They have inbuilt it to enhance the speed of multiplication. So as I said, this core, it talks to the external world in the sense what? The memory, by using a bus called address bus. So this address bus is 32-bit, A0 to A31. So 2 to the power of 32 is the number of memory locations can be there in a memory chip. So using this address bus, I will fetch the data from memory, data in the sense what? In the instructions and the actual data, and get into this core. So every time, so you generate an address, get the instruction, execute it, and then go to the next instruction. So you have to increment the address every time. For that, address increment is provided. So since we know that 4 bytes is required for one instruction, so every time address register will be incremented by 4. First 0, then 4. It will increment. So there is a register, is a specific register in the register bank among the 37 register. One of the register will be called as program counter, PC. So that PC, it generates an address bus here. And then after the one instruction is executed, address incremented take that value, again puts the incremented value here. Now for a moment, we will understand that and come back to here. So let's say I'm going to a microcontroller based software development where I have written some program. It's not required to understand now anything about this program. So only to explain how address will be incremented by 4, I want to show that. I compile this program. I'll compile this program. I have compiled this program. Then I'll execute this program. When I execute this program, the left side, what you can see, it is inside the core. It is all these are present inside the core. That means that all registers. This is the contents of memory, which is not inside, which are outside the core, but inside the microcontroller. Inside the microcontroller, these are all the contents. So these are the runtime. Runtime, I stop my execution. So look at one register called PC, program counter. You can look at that. You can just zoom your window. If you're using mobile, you can just check that. It's called program counter. What is the value of that? 0. So each digit here represents 4-bit because I represent in hexadecimal. Now how many such digits are there? 8 digits are there. 8 into 4, that is 32 bits is the address thrown by the core. Now I will execute the one instruction. So now see that my program is now at the first instruction. What is an address? 0. Now I'll execute one instruction. See that now it is incremented by what? The 4. Now again I'll execute another instruction. So now see that it has become 8. That means that program counter increments by 4 after execution of every instruction. Why? Because every instruction requires 4 bytes in the memory. So every 1 clock cycle, it fetches one instruction. So that will fetches the next instruction by incrementing the 4. So I will go back. So this is the meaning of the PC bus. PC bus is nothing but what? Contents of program counter. Among the 37 registers, one register is called as a program counter, which generates the address. And every time you fetch one, address increments by 4 and put that back into here. And also update into the program counter also. So address incrementer updates the program counter and also put back the incremented address. Incremented address, it is taken where and put it here. So this is about the contents, what is present in ARM7 architecture. So summarizing, if somebody asks what is present in ARM7 means, it has got a 32-bit ALU, it has got a barrel shifter, it has got a 37 registers, it has got a multiplier, it has got an address incrementer, and the core connect to the external world using 32-bit address bus and 32-bit data bus. So 32-bit address bus is used to get the to generate an address to the memory. Data bus is used to fetch the data. So this is how the ARM7 architecture is being designed. Now, so once we have understood what are the basic blocks present in architecture, now it's my responsibility to study in detail about every block, because as an assembly language programmer and as system developer using the ARM microcontroller, unless I study every block in detail, I cannot write the programs in assembly. The person who writes a program in assembly, he should know every detail about the architecture inside. Then only he can be able to write a program in assembly. So this study, so what is called as studying what is present inside the architecture, understanding them, and learning what instructions are supported by the ALU. This study is called as instruction set architecture. So we use a word called as ISA. Now onwards, if you hear this word in the future for any study on a controller's processor, understand that instruction set architecture is the programmer's model of the architecture. What do you mean by programmer model? The programmer who writes a program in assembly should understand what is present inside the architecture. How many registers are there? What is the size? What are the names? What are the instructions supported? So how the stack pointer works, how the program code works, everything you should know the details. What are the flags are provided? So this study is called as instruction set architecture. So now let us go into the instruction set architecture, understands every block of the ARM7. Am I audible?
Yes.
Am I audible?
Yes, sir.
Yeah. Okay. Now we will go to the details. First, operating modes. ARM microcontroller chip. When you give the power, it starts working. So this working can exist in 7 operating modes. That means that whenever you observe the ARM running the instructions or running the program, ARM may exist in any one of the 7 modes, operating modes. It cannot exist more than one mode at a time. Each mode is unique. Either it should be in the user mode, either it should be in the system mode, either in the supervisor mode. So these are the 7 modes it can exist. This type of separate modes also supports operating system to be loaded into the microcontrollers. Because whenever you have an operating system, we have a concept called as kernel program, user program, or user mode, supervisor mode is there. So these type of modes of operation was not there in simple microcontrollers like what used in Arduino board, like an Atmel microcontroller or Intel 8051 microcontroller. It is not there at all, because there is only one mode that is called as you can call them as user mode or you can call them as supervisor mode. There's only one mode. There is no question of segregation. There is no question of privileges for the user and the supervisor. All the code will be visible to all the programmers or all the users of that system. There's no protection is there. There's no protection to protect your OS code. There is no way you can protect only certain people or certain people who are with the privileges can able to access certain registers. No, anybody, any program can modify any register in a normal microcontrollers. In normal microcontrollers, there is no faster response for the interrupt. That means that when you're doing something, some data comes to the microcontroller from external world, some sensor data, you should stop your execution, attend that request generated from the microcontroller, external world. So to support these faster response, to support OS, to support multiple programs, to support the privileges, ARM architecture is designed to work in multiple modes. What are the modes? As soon as I start my microcontroller, always it goes into what is called supervisor mode. So let's understand that. We will go to the program here. I will stop the program now. Now I'll stop the program. Now I will run the program now. The moment I run the program, I set the microcontroller enters into what mode? Supervisor mode. Because I have not written OS code here. In this project, I have not included real-time operating system. I have not included multiple programs. I have not included a startup code, because when you created a project, it has an option of a startup code. I said no. So whenever you don't include the startup code, you're not switching the mode. The mode it enters after the reset, that is the mode you remind. So we will see that what mode it will be there after run some instructions without the OS, without the startup code. So now I'll say debug. Now look at the runtime environment of this one. So this runtime environment, look at all the modes are there. Look at which is dark here. You can just enlarge. You can zoom that. You can zoom that. You can say it's in the supervisor mode. That means that the moment I restarted my project without the startup code and with the OS, it always goes to which mode? Supervisor mode. So that you have to understand that. So whenever you write very small project, no OS is there. So you are always executing the whole of the project in the supervisor mode only. But if your project is little complex, you are able to create a OS-like environment, segregate the kernel code and the user code. Then what will happen is, after the supervisor mode, that is after the reset, you are in the supervisor mode. Then execute a software interrupt instruction supported with ARM. Then, so you, sorry, the other way. After the supervisor mode is entered after the reset, then you can change the mode. That is, all the kernel related jobs, you finish it. Then you switch to the user mode and execute the user applications. When you are executing the user applications, user programs, you can always come back to the supervisor mode to have the higher privileges or to do something in the kernel by executing what is called software interrupt instruction, SW instruction. So how did you enter to supervisor mode? One is through the reset. By default, I'm into the supervisor mode. After reset, so the other is through the software interrupt instruction. So come back from the user mode to the supervisor mode. So we have understood the two modes. So supervisor mode is called as operating system kernel mode. So the user mode is the mode. Normally in this mode, user programs will be run. It is called as an unprivileged mode because you are not able to access important registers of the CPU, ARM7 architecture, and also you cannot able to disturb or access the kernel code. This is the, we call it the unprivileged mode. This is a mode in which user is going to run your programs. So in normally lab, so whenever you write assembly, we will be there always in the supervisor mode because we are not switching to the user mode. But when you write embedded C code, I will include the startup code in the project. I may switch from supervisor to the user mode. I may run programs in the user mode. So keep monitor on the in which mode you are working it. So now we have understood supervisor and the user mode. There's another mode, user mode only, but little more privileged compared to the user mode. That is called the system mode. So we can call this system mode as a privileged user mode because you can able to manipulate and control the activities of the processor in system mode. So there is a register is there present. It's called as Cpsr. It's called as a control register, control program status register. This register contains certain bits. Through that, I can able to control the working of the core. I can manipulate certain operations on the core. This register, if I want to manipulate, I cannot do in the user mode. I can do only in the system mode. Going back to the core here. So you look at the now the registers here. I will just expand that. Current. Now look at that. This is a register, Cpsr. So this contains so much information. It contains about the flags, whether you are in the thumb mode, or a normal 32-bit DOM operation mode. So interrupts, other things, so many things you can able to manipulate and control in the Cpsr. This register you cannot modify when you are in the user mode. So that is the meaning of system mode and a user mode. System mode is a completely unprivileged mode. If you want to access certain sections of the ARM architecture, like modifying the flag register called program status register, you have to switch to the system mode, modify that, and again come back to the user mode. So we have understood now supervisor mode, user mode, and the system mode. I said whenever you work on the microcontroller consists of two things. One is called the core. So this is a core. And this is called as the peripherals. So the peripherals talk to the core by sending what is called certain signals to the core. All this core and peripherals are present inside the microcontroller. That means that microcontroller contains core plus peripherals. Peripherals means what? You have an ADC, DAC, PWM. So you have GPIO pins, you have timers, so many blocks are there. And serial protocols are also supported here. That means that this microcontroller gets the data or the signal from the external world. And also it gets the signal from the peripherals inside. So the core can receive the data either from the peripherals or through the external world, the devices, maybe the sensors and other things. So whenever you receive the request into the core, and sometimes the request can come from different blocks of a core itself. So whenever the core gets the request, either from inside the controller, from outside, the request can be classified into two types. Is it a request very urgent? I should be able to satisfy the request immediately. It's very critical. Or the request can be okay. I can finish my job now. I can just postpone that request for a moment, and then I can satisfy or run the program which can satisfy the request. So almost all the requests which is coming to the core will be called by the name as an interrupt. So interrupt is a request to the core from the microcontroller peripherals or external devices to give attention. So if the request is coming from the faster devices, I can categorize them as fast interrupt request. So it is whose responsibility? As a system designer, as a programmer, you can take a decision. Oh, these devices are important for me. I should consider them as a fast interrupt. These devices, these sensors are not that much of important. I can categorize them as a normal interrupts. So normal or fast interrupts, a system designer or a programmer can take a decision. But the core supports identifying the interrupt and categorize them as into the fast interrupt request or the normal interrupt request. So whenever you get an interrupt, what does the core should do it? Core is already executing a program. There is a memory is there. So there is a memory is there. You have stored your program in the memory. The core is executing the program here. Now you get a request. What the core should do it? If it's a fast interrupt request, stop this program, stop it immediately, and then go to the device which has received the request and attend that device. So that means that you should stop wherever it is executing it. Stop the whole state of the core. Register contents may be something, the flag contents can be something. So there, whatever the values are there in the registers, whatever the values are there in the flags, you have to stop there suddenly and immediately you have to attend some other work. So that means that the mode in which you are there, you should leave that mode and get into another mode to attend the service. Then what will happen? You can easily come back and continue into the old mode. So that mode which is going to enter whenever it receives a request on the faster interrupt request device in the channel is called as a FIQ mode. So FIQ mode, when it is entered, whenever the core receives the request of type faster interrupt type, then it stops the program, leave the mode, whichever the mode, whether it may be in the user mode, the mode or supervisor mode, leaves there, enter into the FIQ mode, finishes the service, and come back to the original mode and continue execution. If the device request is of a normal interrupt request, then it enters into a mode called as IRQ mode, attend the service of the device which has raised the request through normal interrupt request, and then finishes that service and come back to the normal execution. So these are the two other modes to support the interrupts from the devices. Now, we will go to the other two modes, which are called as an exceptional modes. What is an abort? I said, what is the amount of memory supported by the ARM architecture? ARM supports, so I will just go back and come back to that screen. See, this is the total memory supported by the ARM7. How much is that? 4 GB. How do you got 4 GB? 2 to the power of 32. 4 GB is there. So not all the 4 GB is provided in the microcontroller used by the ARM7 core. So microcontroller which uses the ARM7 core. Only, for example, if you take LPC2148, it provides only 512 kilobyte wish. Even though memory is how much? 4 GB. I am using how much? 512 kilobytes only. And they provide 32 kilobyte of SRAM. Even though my total memory is 4 GB, LPC2148 provides only 512 kilobyte of program memory and 32 kilobyte of RAM memory. So that means that these are all empty. These are all empty. These are all empty. So whenever you try to generate an address from the ARM core, that address, there is no memory chip is available. There is no memory is provided. That means that empty space is there. Then what will happen? The exception generates, because you're trying to access a location which is physically not present. It is nothing but getting into a house in a locality where there is no house in the site. You can go and see the site, but there's no houses there. You cannot get into the house. Same way, you have number of locations are there, but memory is present only in certain locations. So memory is put only in certain addresses. So this type of exception, that is accessing a memory location where there is no physically memory is present, is called as abort mode. Used to handle memory access violation, abort is entered or filed memory access. It can be memory may not be present, or memory error also may be there. Memory chip error can also be there. This is called as abort. Undefined. So this is another exception. The 32 bits which is required to represent one instruction. In this 32 bits, not all the bits are used to represent an instruction. Only few bits, maybe more than 16, we will see that. That certain bits are used to represent the opcode or instruction. So there is a valid combinations are there, 0010, 10110, like that. If you try to use a combination which is not a valid opcode, which is not a valid instruction, then what will happen? The core cannot understand the meaning of the instruction. So when that happens, it is called undefined. That means that instruction is not defined in the ARM7, that architecture, whatever you are using to execute your program. So these are the 7 operating modes present in the ARM7 architecture. So what are the modes? One is the supervisor mode, the kernel mode, then the user mode where it's your programs are going to run. System mode, it's like a user mode but little privileged mode. And to support interrupts, FIQ mode, fast interrupt request mode, normal interrupts, IRQ mode. Then to support 2 exceptions, one is abort memory exceptions, undefined is a invalid instruction exception generation. So these source for these 2 is what? So it is happening inside. That means once you fetch the opcode, you are able to take a decision. Whereas these 2 what? Requests coming from the other peripherals are from outside world. So whereas supervisor mode, you're going to enter and then you switch to the user mode. You switch back to the user mode, supervisor mode, and system mode by executing certain instructions like SWO here. So these are the 7 modes supported by the ARM architecture. So let's list those modes and understand that. See, these are the 7 modes. So current mode, that is nothing but the supervisor mode. Then you have a user and system mode. This will be generally considered as a same mode. User and system mode, there's no difference. Only thing is in system mode, you're just allowed to access Cpsr register, control register. So then fast interrupt mode, in the normal interrupt mode, abort, undefined. So these are the different registers and what are the values present in them. So now we'll go back to the architecture. So I was telling that instruction set architecture is what? Study of the ARM core in detail. So now we have studied the first step. What is the first step? The moment you give a power to the microcontroller ARM core 7, it can exist in one of the 7 modes that you have to understand before you start writing assembly programs. Next. So we will go to now very important block of the core, which is nothing but the registers. It is a challenge to understand the different registers, what is present in that. So we will go step by step and understand them. So I will go to the registers one by one. So then we will discuss it. Okay, so look at this diagram for a moment. How many registers are there in the ARM architecture for a programmer? So if you're able to see this, starting from R0 to R15, so 16 registers are provided for the programmer to use these registers in the program. So R0 to R15 registers are there. So that what does it mean is, if I go to my program, I'll stop the program for a moment. I will remove all the instructions what has been provided here, all the instruction. I'll just execute without any instruction to just check that there is no error is there in the code. So there is no error is there. Now let's say I'll use one instruction. So the name of the instruction is the move. So move. Now let's say what is the meaning of this instruction is, I am loading into this instruction a number called 10. Now what are the valid registers here? I can write here R0 to R10, R11, or up to R15. I can able to write it here. See that the color is changed. If I try to write R16, see the color is not changed. That means that it's not supported. You will get an error. So I can write in an instruction R0 to R15. So that means that how many registers are available for a programmer to work? There are 16 registers available. It's called a general purpose registers available for a programmer to use in the instructions. Now, in this 16 registers, there are 3 registers are there, which has a special function. That means that you can use them as a normal register also, but there is a special meaning is assigned to these registers. So what are the meanings and what are those registers? For example, R15 is called as a program counter. We have already understood when we discussed about the architecture. What is the program counter? Program counter is a one which always shows in the memory location, which is the address I have to use in the memory to fetch the next instruction. I showed you that program counter becomes 0 after reset. Then it increments by 4, 4, 4 like that. Every time you finish one instruction execution. That means that program counter is very essential to run your program. Otherwise, you lose the track. You don't know which is the next instruction to be executed. So even though R0 to R15 are available for the programmer to use in the instruction, I will be not using R15. That means that even though it is allowed R15, I am not going to use that. Because why? R15 is meant for a program counter. If I use that, my sequence will be changed. So I will not use even if it is allowed. So if at all, if you're using, you should be very careful. You should know that consequence of that instruction execution. Now, let's go to the next register. It's called a stack pointer. Whenever you write a program is generally procedure oriented. That means that you write the programs in a pieces, small procedures, then keep calling them as and when that logic is required. So whenever you call a procedure, then what will happen? The place from where you're branching should come back. That means that I'm executing a program. Now I want to call a procedure. Then what I'll do is I stop this program for a moment. I go to procedure. I finish the procedure. I'll come back. So that means where is my return address? So return address will be stored in the memory. So that memory will be called as stack. We know that. Or whenever you want to pass certain data to a procedure, we push the data into a stack and then go to the procedure. There in the procedure, I'll access the data from the stack. So as you know that stack is very important block of memory or important logic, which is extensively used for data exchange, for storing the return addresses, for so many other important programming related jobs. So whenever you want to use stack in your programs, so you should be able to keep track of stack. You would have studied in the architecture and also in the data structures. Stack always associated with the stack pointer, which always points to the top of the stack. So if your stack is implemented in your programs, don't disturb the R13 because R13 is meant for a stack pointer. If you're not using the stack in your programs, you're free to use R13. So what I mean is, so in this, I can use R13. When I can use 13, if I'm not using stack in my projects. If I'm using a stack in projects, don't use the R13 because it is meant for a special application for which you have to use it. The most challenging and the most novel concept of the ARM architecture, which has been introduced, which was at that time no other microcontroller supported, is called as link register, concept called link. Just now I explained the concept of a stack. But to understand that, you should be able to know that how exactly accessing the stack requires more time. For example, if I am executing a program, so don't look at these registers for a moment, just look at them. See, let's say this is my core, that is a core, and this is my memory. Both are not present inside a single block. That is, they are separate blocks, they are connected, and they are present inside the whole chip microcontroller. When I say stack, where is the stack is there? Stack is inside a core or stack inside a memory. You should be very clear with the fundamentals. A stack is a set of memory locations. It is not present inside the core. When I say stack, it's always a part of the memory, which is not inside the core. Then what will happen? Whenever you call a procedure, that means that you are executing a program, you stop the program and you branch to a procedure, then what you do is you have to store this address, this return address into the stack. That means that since stack is outside the core, you have to go outside the core, execute an instruction to store in a memory. Then when you come back from a procedure, you go outside the core, fetch the content from the stack, and then continue. It takes a lot of time because what? You're trying to do certain things which is outside the core. So it consumes a lot of time. So to support the faster access or faster execution of the procedures, they have said that don't use the stack. Now I want to go from here, that is I'm executing a program here. I want to go to a procedure. I want to branch from here to here. Then what should I do? The return address, keep it somewhere inside the core itself. Then what is the size of the return address? We know that every address is 32-bit. So that means I require a register inside the core which can hold the 32-bit. So that register can be accessed inside the core. Since it's inside present is there, I can just store it inside and then I can branch to a procedure. I can branch back from procedure to the normal program, fetching the data from that register. So this link is required. Link between what? The procedure and the main program without having the stack. But the effect of stack should be there. the purpose of stack should be implemented without using a stack. So that is done by a register which provides a link. That register is called as a link register. This is really a very good concept. So present inside the ARM architecture, which enhances the execution speed of your programs, because you need not go to the stack to store the return address. It should be there inside the core itself. That is called link register. So again, as a caution, if you are using the procedures inside your projects, don't use the R14 as a general purpose register, even though it is supported. So when I use a move, even though R0 to R15, I can access them, but I generally, as a programmer, keeping caution, I will not use 13, 14, 15, because they have got a specific functions called as a program counter, link register, and a stack pointer. Now, how many registers I have for a programmer? Effectively, I have R0 to R12. So you can use these registers for keeping what is called as your data and addresses also. Each of these registers is 32 bits. So how many registers are there for a user to write programs in the user mode or system mode? 16 registers are there. In that, 3 registers has a specific application. 13 is called stack pointer, 14 is called link register, and 15 is called as a program counter. Link register does not remove the necessity of a stack pointer. You should understand that. It's only one level branch you can able to store it. If you want a multi-level nesting or pushing a lot of data in stack, then memory is required. So one level, you can always use a link register. So these are the R0 to 12 are the general purpose registers. The size of each of the register is 32 bit. I can use that for either storing the data or for the address. So this completes today's discussion about the instruction set architecture of ARM7. So we will continue in the next Monday the balance of the ISA architecture discussion. So